In this problem, we're asked to solve for what is the moment of inertia for about the x-axis for the circular area. So, for this problem, we have to first define what is the equation we're going to use. So we're going to define our element, and we defined our element here, a differential element dA, and we notice that dA is parallel with the x-axis. So since it's parallel with the x-axis, we can say that I of x will be equal to the integral of y squared dA. Okay. So the next thing we need to determine here is what is our dA, what is our differential element, what is it equal to? So how can we define dA? So we know that dA is going to equal to 2x, so 2 times the x coordinate. So we have positive x and we have negative x. So the total length would be equal to 2x. And then we have that 2x gets multiplied by dy. Right. So if we plug all of this in, what we end up getting is we get I of x is equal to the integral of y squared times 2x times dy. Right? So we have to relate x to y. Right? So we know that the equation for a circle is equal to x squared plus y squared is equal to the radius, or in this case a, the constant a squared. So we know that that if we rearrange this equation to solve for x squared would be equal to a squared minus y squared, and x would be equal to the square root of a squared minus y squared. So once we have that, we can plug that into our equation over here. So we end up getting I of x is equal to I of x is going to be equal to the integral of y squared times 2 times the square root of a squared minus y squared dy. Right? So this integral here will go from the bounds of our y integral. So y goes from the negative radius to the positive radius. So we'll have our bounds of our integral will be minus a to a. And then we can integrate this equation. We're going to just bring out the constant, the 2 constant. And then we'll end up with this equation here for y squared times a squared minus y squared dy. Now, if we look up the integral table from the previous lecture, all right, we know we can look up what the heck, what this integral would be equal to. So if we do that, we find out that I of x will be equal to 2 times minus x over 4 square root of a squared minus x squared cubed plus a squared over 8 times the x times the square root of a squared minus x squared plus a squared times the sine of negative 1 x over a. All right, and this whole thing in the square brackets is going to get evaluated from a to negative a. All right, so if we plug, this looks really ugly, but what happens here is if we plug in a to x squared or negative a into x squared, we will we'll get a squared. And then for this term here, and this term here, if we plug in x is equal to a, and when x is equal to negative a, what we end up getting is we get a squared minus a squared, which is equal to 0. So we end up having both of these terms here due to this condition will both end up being 0. So our equation will simplify down to just being equal to 2 times a squared times the inverse sine um, of a over a minus a squared times the inverse sine of minus a over a. All right. So if we look at that, we end up getting 2a squared times the sine of negative 1 of 1 minus the arc sine or the inverse sine of um, negative 1. So we know that the sine of an angle is equal to 1 at pi over 2, and we know that the sine of an angle equals negative 1 at negative pi over 2. So what we end up getting is we get 2a squared, I of x is equal to 2a squared times the sine of negative 1, or sorry, the sine of negative 1 is equal to pi over 2, and then the sine of inverse sine of negative 1 was equal to negative pi over 2. So this ends up getting equal to just pi. So we end up getting 2. I messed up somewhere. Oh, I'm sorry. I forgot to include this a squared over 8 term here. So this should be so this 2a here, instead of being 2a squared, it should be equal to 2a to the 4th over 8. All right, that looks much better. So this will end up getting to just be equal to pi times a to the 4th over 4, which is, if we substitute in pi a for for r, what we can say is that the I of x for a circle would be equal to pi r to the 4th over 4, right? Which is, if we set that r is equal to d over 2, we can say that this is equal to pi d to the 4th over 64. So since this is symmetric about the x and y axis, we could also say that Iy would be equal to pi over 64 d to the 4th as well. And since we know Ix, J polar moment of inertia is equal to Ix plus Iy, we would know that this would be equal to pi over 32 as the diameter before. Okay. All right. So just in summary here, we defined our element, differential element dA in terms of our variables. We then broke this into, wrote this all in terms of one variable y, and we integrated along the bounds of our integral. We rearranged our integral so it matched a common integral that we can use an integration table to solve. And once we had our integration table, we plugged in our two values, and we realized that most of our terms canceled, and we were left with just the the um, the inverse sine term, and we just solved all that out. And when we did, we ended up with our answer. All right, so most of these problems are just integrals. The main thing is just knowing how to set up the integral in order to get the correct answer. That's all. All right, and that concludes this problem on moment of inertia of a circle.